Okay, let me remove this. I will first review a little bit some of the main tensions that exist right now in this other model, which has been a very successful model, of course. But there is still some disagreement, which is becoming more and more significant as time goes by into some important parameters of the model, which seem to have the conflicting values among different observations. And the most well-known, of course, tension is the well-known Hubble crisis, I would call it now, because it has reached the 5 sigma level. Of course, depending on which probe you have, it really depends. It's about 2 to 5 sigma level, depending on the probe one uses to measure it. Local measurements of H naught are right now at about 5 sigma tension with the CMB indirect measurements of H naught. For example, the sound horizon as a calibrator is actually now in conflict with local calibrators, and mostly those local calibrators that are based on Cepheids. And as you know, we have this conflict between 67.4 for the CMB and BAO and measurements compared to 73.04 plus or minus 1 kilometers per second. It is a 5 sigma tension, about 9% difference between the two values. Now, there are also other tensions which are less perhaps well known and less significant, I would say, but they're still important. There is the growth tension, which is a 2 to 3 sigma effect between the direct measurements which probe the growth rate of cosmological perturbations through gravity and through gravitationally bound systems or linear fluctuations of gravity, and compared to this anticipate based on general relativity result coming from the Planck lambda CDM best fit model, which seem to indicate that the local measurements which probe directly gravity indicate somewhat a weaker growth rate of fluctuations than it would be anticipated from Planck lambda CDM based on the standard parameters of the standard model. So there's also the well-known cosmic dipoles tension, which is various types of cosmic dipoles on very large scales, which seem to somehow violate perhaps the cosmological principle. They also have been a focus of many studies during the past few years, and these dipoles also seem to be amplifying the tension with the cosmological principle during the past few years. And also, of course, there are the well-known CMB anisotropy anomalies, which also include some peculiar features on the cosmic macro background fluctuation maps. And they also have been an issue of discussion during the past few years, and indicate, along with the cosmic dipoles, some hints that maybe the cosmological principle may not be valid and may need to be modified. So the question that we have therefore is, using all these anomalies, what could be this telling us about fundamental physics on the basic assumptions? What would be the physical laws that perhaps we would need to change in order to be consistent with all these different tensions? And not only these, I would say there are many other more tensions which are less known, and all these tensions are discussed in this review that we have recently published in 2002, about a year ago, which is known as Challenges for Lambda CDM and Update. This review summarizes these tensions and tries to put them in a way that would be a combined and comprehensive way to view them, so that one can deduce some possible physics changes on a fundamental level by combining them at the same time. So let me briefly review now the Hubble tension, which you probably all know. We have a wide range of probes of the Hubble parameter using all these different approaches, and they seem to be clustered on two regions. One is the region of around about 67 kilometers per second per megaparsecs, and the other is about 74 kilometers per second per megaparsec. The one is based on a calibrator based on the sound horizon of glass scattering used as a standard ruler, and the other is most accurate ones are based on supernovae, on the absolute magnitude of supernovas calibrated using mostly Cepheid stars, which is the most accurate way to the most precise, I should say, not necessarily accurate way to calibrate distances and therefore measure the Hubble parameter. Of course, there are lots of other intermediate measurements which seem to be consistent with both sides, but these are less precise, and so the tension is based mainly on the comparison between the Cepheid calibrator of supernovae absolute magnitudes and the sound horizon scale at last scattering, which is used by as a calibrator for CMB measurements, for baryon acoustic oscillation measurements of the Hubble constant, and I will discuss them later in some more detail. Here you see also these measurements, and you see they are also clustered around this value of 67 around here, and this value of 74 for this Cepheid. But of course, there are also additional other measurements. Now, these are the late time calibrators based on late time measurements, and these are the early time calibrators. You see most of the early time calibrators are focusing, are resulting to an H node around 67, and the late time calibrators result on H node around 74. However, there are some late time calibrators like the cosmic chronometers and the gamma ray attenuation, and also the gravitational waves, at least this imprecise measurement we have, which seem to favor the early time result of 67. So it's possible that it's not a comparison between early and late times, but it's some different feature of the measurements which should be used to classify these these measurements favoring either a low or a high H node. So the big question is, what is the feature that distinguishes the two groups of these H node values, of the Hubble parameter values? Is it cosmic time, or could it be the assumption of some other assumptions, like the assumption of some difference between high redshift or low redshift gravitational physics? That's one issue one can think about, and in constructing models about the explanation of this strange and interesting tension. Now, the other tension is the growth tension, which basically indicates that the growth rate of fluctuations is predicted to be different when it's probed directly by various probes and when it's probed indirectly through the parameters of ΛCDM as obtained from Planck from CMB measurements. And here you have, for example, the redshift space distortions, which use peculiar velocities to probe the growth rate of fluctuations at various scales. And you see, for example, here that this parameter sigma 8, which essentially measures the strength, the efficiency, the growth rate of fluctuations at various cosmological times, seems to be lower when it's probed through the peculiar velocities, the observed peculiar velocities of galaxies, and compared to the value that one would anticipate based on parameters from Planck. So you see there is some tension, not very significant, but the 2 to 3 sigma tension from redshift space distortion from peculiar velocities effectively observed through redshift space distortion. A similar observation exists when we have the gravitational lensing, where you see here the various gravitational lensing probes. This is the KIDS measurements, and you see again that the product sigma 8, this S8 parameter, which is this degeneracy line here, appears to be below the corresponding value of sigma 8 probed by as essentially favored by Planck. And we see again the same effect, that the gravitational growth rate as probed directly through gravitational lensing is less than the corresponding strength of gravity or its corresponding growth rate as probed by Planck in the context of the standard cosmological model. So it looks like some mechanism seems to be producing weaker growth of fluctuations than anticipated in the context of the standard cosmological model. The same effect is observed when we use cluster counts, measure clusters, a number of clusters as a function of redshift. One actually obtains the same effect of weaker sigma 8, which is along this degeneracy line, compared to the sigma 8 obtained directly through the direct measurements of Planck of the CMB in the context again of the standard model. So three distinct and independent probes of gravity and of the growth rate of fluctuations seem to be in conflict or in some 2 sigma conflict with the anticipated based on the standard model. Now the cosmic dipoles also is another issue which is puzzling, which we have the observations of bulk flows on various scales, which from this reference here by Watkins, Colling et al., which indicates that this is the main plot, that the observed bulk flows or bulk velocity flows on large scales as a function of the scale here appear to be much larger than the predictions. This is the red line, the prediction of the standard model. And so the question is what induces these large velocity flows in these anisotropies on very large scales. And this is one of the puzzles to see if in fact the cosmological principle is somehow needs to be reformulated. Similar observations exist from the quasar distribution in the sky, which seems to be anisotropic, and there seems to be a dipole of the structure of the distribution of quasars on large scales, and this is the observation here, this line here, and this is actually the prediction in the context of the standard model. You see that we have a 5 sigma difference in the prediction. There seems to be some anisotropy in the distribution of the quasars compared to the predicted based on our simple velocity with respect to the CMB. We would have, of course, some anisotropy. We expect it, but what was observed is much bigger than the anticipated. The direction of this dipole is we see very close. This is the direction of the dipole, the QSO dipole, and this is reasonably close to the CMB dipole direction due to our velocity, which we think is due to our velocity with respect to the CMB. And this is an interest that we have this kind of similar direction. The same dipole is observed, a similar dipole is observed using the distribution of radio galaxies. And you see here, for example, the dipole component as a function of the angle theta with respect to the whole sky. This is the theta corresponds to 0 corresponds to the whole sky, and while theta less corresponds to taking a strip around the galactic around the equator of this dipole, around the theta equal to 0 angle, and you see that as we approach the full sky, theta equal to 0 angle, we see that the dipole becomes bigger based on various samples, and you see that there is a tension compared to what we would anticipate from assuming that the only anisotropy is due to our velocity with respect to the CMB, and that's a puzzling also 3 to 5 sigma similar anisotropy tension with respect to the anticipated. So we again have two anisotropic distribution of both radio galaxies and quasars. And so where does this dipole come from? And you see here various other dipoles from this very interesting paper. I recommend it highly because it summarizes very nicely the various dipoles that have been observed so far. You see here that most of the dipoles are concentrated. This is for example, this is the QSO dipole in this direction here in the sky. We also have the radio galaxy dipole. We see it's also very close here, and also the bulk flows dipole here, and the CMB dipole is right here in this point. So you see all these dipoles are more or less directed in a similar area in the sky. This is the opposite region on the other side. And so it's a question, and all these directions are close to our CMB dipole. So maybe the CMB dipole may not be just due to our velocity, as it's usually thought, but may actually be due to some other fundamental reason, which can be understood by combining all these dipoles. So the question is there some kind of model which can combine all these tensions and try to give us a new physics change which would resolve simultaneously all these tensions. So we have so many tensions at the 5 sigma level, or something like close to that, to 3 to 5 sigma level. And despite of this tension, we still think that lambda CDM is our standard model. Why is this perception happening? One reason is due to inertia. People tend to like the model which has already had so many successes, so many other successes of the model, and so people have a tendency not to abandon a standard model. Historically, this is a tendency which exists. The second and most important, I would say, reason is that there is a lack of a simple alternative model. In all changes of standard models so far, there was a clear alternative which was also simple and physically motivated. In this case, we do not seem to have such a simple model. So lambda CDM remains standard model not only because of its success, but also because of its simplicity. There is no simple alternative which is also physically motivated. And also that there are too many tensions, as I said, there are also other tensions compared to what I've said, which seem to be, from a first point of view, somewhat unrelated. And so it's maybe difficult to construct a coherent model which is also simple and addresses all these tensions. So let's compare this with previous changes of the standard model to see what happened in the past and what is likely to happen perhaps also now in some time, in a few years, perhaps in the future. Now, a very major, of course, change of standard model is the change from the steady state model, which went to the Big Bang theory. At that time, in that case, of course, we had this discovery of the Hubble expansion. It was very clear observation, and there was a very simple alternative based on the Big Bang model, which had very well defined theory, Friedman equations. It was a simple and obvious alternative to the steady state model, even though it was not very appealing to the common sense of many people. So the existence of an alternative simple model allowed us to have a change of standard model. Next, in the early 90s, we had the change of the simple CDM model, ＳCDM, to the lambda CDM, which included just one more parameter. It was very well motivated. So for that we had the data. Of course, there are lots of data appearing, but at smaller tension level, as you say. In that case, the tensions were not so strong as they are today. But the important thing there was a simple alternative at the time, and it was also physically motivated because the cosmological constant was motivated from inflation. We had various reasons to believe that it had some reason to exist, and we had some early time approaches by Peebles 1984, Eustathiou 1990, and also Krauss and Turner 1995, which clearly used the tensions that existed at those early times, which were on the age of the universe. These tensions were the matter power spectrum, which indicated an open universe, a universe with lower matter. The matter that was observed directly was less than the matter of the SCDM model. It favored in those days somehow less matter, and also the peculiar velocities. And these low significance tension allowed, however, these people to point out early enough that perhaps we need a new simple alternative to SCDM, which turned out, of course, with the supernova observations of 1998 to be, in fact, the correct model, the model to replace, in fact, this better model, I should say. So what are the new simple replacement of lambda CDM that will release most of the tension with just one or two parameters? Are we viewing the same scenario again? And can we predict somehow the next model using these historical observations and introducing one or two new parameters? To do that, we need to actually understand deeply these tensions and the origins of the assumptions hidden in these tensions. So understand both the data. The data is the most important guide to understand the tensions, and this data will guide us perhaps to the upcoming better model, which should also, I said, be simple. So let's try to focus a little bit as an example to the Hubble tension, because of course I don't have time to focus on all those in some detail. I will focus on the Hubble tension to try to understand it a bit in more detail. How do we measure the Hubble parameter using standard candles, the supernova standard candles? We use this data, as we all know, in the redshift range between 0.01 or 0.022 and Z 0.1. We start with the observed apparent magnitudes of the supernova, this quantity here, which is connected with the luminosity distance through this well-known relation, and the absolute magnitude, the luminosity, the intrinsic luminosity of the supernova through this relation. And then using the connection of the luminosity distance with the Hubble parameter and defining also the Hubble free luminosity distance, we can write a relation which connects the observed apparent magnitudes of supernovae with the absolute luminosity, the Hubble free luminosity distance, and the actual Hubble parameter itself through this relation. And the name of the game is, of course, you see that there is a degeneracy between M and H naught. So the luminosity of supernovae with the Hubble parameters have some degeneracy through this parameter calligraphic M. They appear in the same way in this fundamental basic relation. And this DL probes actually the expansion rate at low redshifts. So the idea is we measure the apparent magnitude. We also measure locally using the calibrators, the Cepheids, this absolute magnitude. And then once we have these two, we also model this DL of Z as a cosmographic expansion here through Q naught, the deceleration parameter. And then so we have to fit now Q naught and H naught, and then we can actually measure the Hubble parameter. But of course, the assumption is that we have to measure locally the absolute magnitude of the supernova. So this game actually shows that in fact there is a degeneracy between M and H naught. And in fact, in this approach, there is no dependence on the Hubble expansion rate, because we are Hubble expansion rate at low redshift, Hubble free expansion rate, this E of Z, because we approximate this at low redshift as a cosmographic expansion. So lambda CDM doesn't enter this derivation. It's independent of lambda CDM, but it's dependent on the absolute magnitude of the supernova and the way they are calibrated. Now, the same game can be played on higher redshifts, and we can obtain, of course, as we all know, the H of Z at higher redshifts. We assume lambda CDM form for H of Z square, and then we make a chi-square fit and fit the parameters omega 0 matter and this calligraphic M, which is the degeneracy, the combination of M and H naught. And this can easily be fit using cosmological large reds, high redshift data. But the important thing with high redshift data, we cannot probe directly H naught, but we probe the combination between M and H naught. So this degeneracy is an important thing to keep in mind. Now, if we go to the standard ruler approach, the early time calibrators, using the sound horizon, the last scattering, we use the sound horizon at recombination as a standard ruler. This is the early universe standard ruler. We have this standard ruler, this sound horizon scale at recombination. We measure this angle theta s using both the CMB and similar the Baron acoustic oscillations. So we have here the measurement based on the peaks of the power spectrum of the CMB. You see how theta changes if we change this spectrum. So this is well measured by the CMB. It's also measured well by the baryon acoustic oscillations, as this feature here in the spectrum. So we measure this theta S using both baryon acoustic oscillation and the CMB. And then we can calculate this sound horizon under some assumptions about what's happening just before recombination. So we have this equation that calculates RS from the Hubble expansion rate just before recombination. Basically, this is the decoupling scale factor here. So this is usually obtained by making the assumption that we know the baryon density and the photon density and the standard and the CDM, the matter density just before recombination. If we know this correctly based on the standard model, then we plug it in there and we calculate RS. And if we know RS, then we can use the relation that connects theta S with RS and with the angular diameter distance. This angular diameter is up to recombination. We use this relation here. We calculate RS using this assumption that I said before. And since theta S is measured, we can use this relation, which uses this integral here for E of Z, which is the Hubble free expansion rate between the virial times and the decoupling, time of decoupling. And you see here that since this is measured, this also can be calculated using the standard model. We can RS is also is calculated. We can infer H naught through this degenerate combination H naught times RS. So the same game can be played with baryon acoustic oscillations, but of course in that case theta S would be replaced with theta bow, and this redshift here will be a much lower redshift. It will not be up to decoupling. So there is a degeneracy therefore between RS, the sound horizon, and H naught, and the better, of course, we calculate RS, the better we know H naught in this approach. Now, one can actually now try to change RS, make RS somehow smaller, so that this increases H naught, and this RS can be made smaller if we assume, for example, that there is early dark energy or new fluids at early times before recombination, so that this Hubble parameter changes and therefore changes RS, decreases RS. And so by decreasing RS, we can increase H naught and make it consistent with the value that one obtained by local measurements. This is the name of the game for these early time models of the resolution of the Hubble tension. So what is the thing that we need to change now? Is this the M, the supernova absolute magnitude, or it's RS? Because we have these degeneracies here, which we have to pay attention to separately. So we have these parameter combinations, this calligraphic M, which is a combination which is measured directly using the cosmological measurements, the supernova on cosmological scales, which is a degenerate combination between M and H naught. And also we have this degenerate combination between RS and H naught, which is also measured independently using again the cosmological expansion rate, Hubble-free cosmological expansion rate at late times. So we measure this M using measuring this parameter here, which these are measured, of course, and these also can be fit, this Hubble-free luminosity distance, and also this also is measured through theta S, which is measured, and through E of Z, which is fit using cosmological data. And so this part is well known, well measured, and both the calligraphic M and RS are very well measured, accurate. There's no tension here. So the tension is between the calibrators, between M and RS. Currently, so therefore, it's more or less clear that one of them has to change. Either M or RS has to change because to make this H naught measurements consistent. So it's in fact a difference between these two calibrators. It's not really anything to have to do with this calligraphic M and calligraphic R, which are based on the background expansion, Hubble-free background expansion, which is very well constrained and measured. Now, recently there has been an additional standard ruler at early times, which is the horizon at matter equality, matter radiation equality. Now, before I go to that, let me state that this is measured with ultralight calibrators, the Cepheids, and this leads to this Hubble parameter that we all know from Rees paper, this Sue's paper, which is this value here. And also, this is also measured from the CMB, as I said before, which leads to this value here, which we see at this point. So this is the paper. Now we have another calibrator, however, which is at the time of equal matter and radiation, this R equality. This is another standard rule, which also tends to lead to a value which is identical or almost identical with the sound horizon calibrator. And this is from this paper by Alicia Verde and collaborators, which seems to also show the same, hints to the same kind of value for H naught. So if one wants to change the early time physics, one has to be careful to change both the sound horizon scale and the time of equal matter and radiation scale, so that they both shift towards this value, which is obtained from the supernova, from the early time physics. And that's a little bit more difficult to achieve because you need a fine-tuned model to achieve both calibrators to shift to this early time calibrator. Alternatively, one can change M and try to make it consistent with this early time calibrators. So the M tension, therefore, can be somehow summarized as follows. We have this combination here, H naught times Rs, and which is measured, as I said before, and this lead to this value of H naught from the early time calibrators. So we can calibrate now the supernova not from Cepheids but from this H naught by using this parameter here, M calligraphic M, and this which is the general combination that I said before, and also which is measured at Z larger than 0.01. And combine this with the measurement of the CMB for H naught, we can infer a value for the absolute magnitude supernova calibrated now not from Cepheids but from the CMB, and this value of M is smaller than the corresponding value of M obtained from Cepheids. So this shows the M tension, as I said before. But the important thing to notice is that this is measured using the Hubble expansion rate and the RS and the sound horizon, which are both at Z larger than 0.1, and this is measured from Cepheids, which are observed at redshift less than 0.01, that is below the Hubble flow. And so this leads us to the M tension, or one could say could lead us to something called the M transition. Since these are measured at different redshifts, one could infer them and assume that there is some kind of transition between the two. This is discussed in these papers here that I'm mentioning. Now, the Hubble tension emerges from this M tension, as I said, using this measured M calligraphic from Hubble and from this this supernova absolute magnitude from the Cepheids, and this leads us to the well-known Hubble tension, which is this one here. But it's actually based on the M tension and not so much on the independent direct measurement of H naught. It's really a tension between M from the inverse distance ladder and M from Cepheids. So the obvious way now, one thing to point out is that M depends on gravity, on the value of the strength of gravity, on G effective. So if there was a transition of M, this could be somehow connected to our assumption that gravity is the same before the Hubble flow starts, before 0.01 and after the Hubble flow starts. So there's an assumption about G effective. So one can construct the hypothesis of an M transition, that is M somehow changes at a redshift about equal or less than 0.01, and we have this transition, which could be due to fundamental physics transition or due to a gravitational transition occurring at about 0.01. So these are the papers where this is discussed. These are the inverse distance ladder values of M, and this is the direct measurements of the luminosity of supernova. And you see this conflict, which is at different redshifts, so a transition could actually resolve this. Now, based on this, we have various approaches to the Hubble crisis. You see here, for example, this is the point measured from the late time measurements, and this is the well-known graph from the early time measurements. You see that the two are in conflict. So the question is, how can we make this consistent? And one can either somehow shift this point down by somehow assuming that M is not correctly obtained, or that there's a transition in the absolute magnitude. So this would bring this point down. Or one can bring this whole curve up by somehow assuming that physics are not the same before recombination, and so we have to shift to change both the sound horizon at recombination and the horizon at time at the time of equality up, so that this would bring this curve up. Or we can deform this value by assuming that E of z, this Hubble expansion rate between the time of recombination and now, has changed. But this approach has now been in disfavor by most people, because we have very strong constraints about the expansion rate between recombination and today, coming from various data. So this third approach now is not so much favored by most people during the last couple of years. And so one focuses on these two, that is early time and ultra late time approaches. So, and it looks like an abrupt transition event may be needed to resolve this tension, because we don't want to touch anything in between the redshift Z0.01, which everything is very well constrained, and recombination. Anything that which is not abrupt, which is smooth, would tend to change also this Hubble free expansion rate, which is here, and so this would create conflicts with data. So we have to do something abrupt either before recombination or after the time when the Hubble flow starts, that means below redshift 0.01. So is such a gravitational transition consistent with the data? Then is the question, and of course it's consistent because data constrain the time derivative of G effective mostly, and not so much the absolute difference of values between early and late times. Are there hints for this transition? As I will discuss, in fact, there are some hints using both Cepheid, Pantheon Plus, and Tully-Fisher data. One can see our recent work on that. Are there theoretical models that can generically induce this? The answer is yes. In fact, there are some models which we have discussed recently, and in fact can induce this kind through a first order phase transition of a non-minimally coupled scalar field, which we have discussed recently. And also there are other ways to do it using topological quintessence, for example, like inducing some inhomogeneous scalar field, which is inhomogeneous due to topology as a Hubble scale topological effect, which can induce these kinds of effects. So I will very briefly mention this. For example, this is scalar tension theory, which could in principle have a potential with a false vacuum, which induce a transition at late times, and this transition could in fact lead to this kind of change of gravity at late times, an abrupt event. Or one can use topological quintessence, which would be a global monopole with Hubble scales, which could also lead to inhomogeneities of the dark energy, leading to cosmic dipoles and at the same time changing some gravitational physics. Now, I will not have time to elaborate more on that. I would be glad to discuss possible questions on these models if there is some interest. Now, what does the Pantheon Plus dataset have to say to us about this possible transition? Now, this Pantheon Plus has a 1700 type 1a supernova, and they provide the redshift of this supernova, the apparent magnitude of them, and also for 77 of them, they provide the distance modules directly measured, not from cosmology, but from Cepheid. That's a novel feature of this dataset, which allows us to simultaneously probe both H0 and the Hubble expansion rate at the same time. And these are the reason is that these 77 supernovae which reside on Hubble on Cepheid hosts, and therefore they provide to us the directly distance modulus. So this therefore can also allow us to provide the Hubble tension. Previous data like the simple Pantheon did not provide this distance moduli from Cepheids. So one would have to do the standard fitting, which we had only distance modulus based on models, based on ΛCDM. And so the standard, the Pantheon, the simple Pantheon fit involved this kind of minimization, this kind of chi-square minimization, where DL was assumed to be of this form. And we had the H of Z model, that's some dark energy model. We had this calligraphic M hidden in this combination between N and M node and H node, which was hidden in this new model, in this model distance modulus. And so there was a degeneracy between H node and M through this standard, this previous approach, and one panel could only probe then this calligraphic M alone, and also could probe perhaps omega matter and 1 minus omega matter, which was assumed to be here through omega lambda. This was the previous data. Now the new data give us, in addition, this Cepheid distance moduli, so it allows us to fit this calligraphic M independently from this not calligraphic, this distance module, this absolute magnitude independently, so we can actually probe directly the Hubble parameter by breaking this degeneracy. Now, in the Broad et al. Analysis, they don't explicitly show this calligraphic M, but we discuss it independently in this paper that we recently have published in monthly notices, where we actually reanalyze this data using the independent information, by extracting independent information about the absolute magnitude of supernovae, which is not done by this in this original paper by Broad et al. So when one does that, one breaks the degeneracy between H node and M and the absolute magnitude for this, at least using these 77 data points. And one ends up therefore by to fit all three parameters, this Hubble parameter here, omega zero matter, and independently fit for the absolute magnitude of supernova. And that's a major difference from the previous Pantheon dataset, which did not allow this independent fit of M because it only didn't include this very valuable data about the distance moduli of Cepheids. So this is very nice. So we have a new, more powerful data set which can probe M also at the same time. And so next we can actually generalize the analysis and say, what would happen if we had allowed M to have two values? Is there a transition here? We can actually use Pantheon Plus to probe this transition directly and allow M to have two values, one value for M less, for D less than decreed, one value for D larger than decreed, some critical distance, which is of course also a parameter, it depends what the data will tell us what is decreed. And you can connect decreed with the distance modulus M crit through this relation, so it's the distances are inside the data already. So we have this new likelihood, which involves two new parameters, M less and M larger, depending on the value of distance for this distance moduli for this data. And we ask the question, is the quality of fit of ΛCDM better by using this new parameter, essentially, these two new parameters, because decreed and new parameter for M? And if it is better, then are these two consistent with each other and with the best fit of the standard likelihood of the single M? So we did that, and when we saw that, we were initially thinking that they would be consistent. It turns out, surprisingly, we saw that they are not consistent at all. There is an inconsistency beyond 3 sigma between M less and M larger compared to the simple fit, the standard fit, which has a single value of M. And in fact, there is a significant improvement of the quality of it by delta chi equal to minus 19. And in fact, there is also a significant tension between M less and M larger due in this context. So we were very surprised to see this improvement. So it looks like this likelihood is really wanted by the data. Also, the value of the Hubble parameter seems to be slightly different, well, not inconsistent, but at least somewhat different if we use this new likelihood. So the better fit this tension between these two M's, and also we have a somewhat so this is the change of fit, and also there is a change of H, shift to somewhat higher value, not lower. That's interesting. But omega zero matter is consistent. You see, omega zero matter doesn't change the best fit whether we use the new likelihood or not. So the cosmological parameters seem to be not so much affected so far with this. Of course, we can use a different model and see if they are affected. But for lambda CDM, omega zero matter is not very much affected with this new likelihood. So does this model affect best fit of other cosmological parameters? That's a question which is open. We have not yet addressed it for general models, but it's an interesting question to address in future studies. So what is the origin of this change? Is it systematic? Is it new physics? Is it both? Now it turns out that in fact a big part of this is due to some systematic effect which is well known, but it's uncorrected in the Pantheon Plus data, and it's known as volumetric redshift bias. I will try to summarize very briefly. Now, if you have some peculiar velocities at low distances, imagine you have three shells of galaxies, one at some distance d, one at a distance d smaller, and one at distance d larger, and you have some peculiar velocities which will be either towards higher values of redshift or away from mass or towards the observer, and these tend to project these layers to either a lower layer to a higher distance and a higher layer to a lower distance, and they tend to somehow bias the project somehow higher layers to lower distance and lower layers to higher distance. And the key point is that because of volume effects, there are more galaxies. You see, this shell has a bigger volume than the lower shell, so there are more galaxies projected to lower shells than compared to those to lower distance shells compared to these higher. So the distance is biased somehow, and so there are more galaxies in the outer shell than the other due to larger volume, and this induces a bias in the distances effectively. And this is one reason that this, and this is also shown in this paper by Broad et al. This is the effect here, and so one part is due to this effect. Now, the question therefore is this volumetric redshift bias, which tends to induce this difference of distance moduli. I will not have time to go in any detail in that. I have shown this in these transparencies. And so we expect because of that some this kind of effect. Is it this whole? It is the only reason for this effect is the question. Now to do that, we can actually somehow remove all the data from Pantheon plots which are due to are at redshifts less than 0.01, where this effect is important, and also allow only for the Cepheid distance moduli on these distances, on these low distances, and see if the effect remains or not, because normally it should disappear. If this effect is only due to this bias, it should disappear once we remove this data. But we see that the effect to a large amount remains here. Of course, it's reduced in significance, but it remains this conflict. We see we removed all the redshift data, the Hubble diagram data on these redshifts, which could induce, of course, this bias, and we see that the effect remains, but to a lower significance. Now it's between about 2 sigma or 3 sigma, depending on the viewpoint that one uses. So there is some tension there, and let's go to the real luminosity of supernova and see if this effect is there. And you see here is the Hubble these are the luminosities of the supernova based on the SUS data now, and from also shown in the Pantheon Plus data. And this is the difference between the apparent luminosity minus the Cepheid distance modulus. So this gives us the absolute magnitude of the supernova. And you see it by eye that all the supernovae that are at distances less than about 20 megaparsecs, which is this best fit critical distance, appear to have a lower M, that is a higher luminosity, compared to the best fit M for all the supernovae which are in Cepheid hosts. And so it's clear from here, at least part of this effect is due to this actual luminosity of the supernova. And then one can actually try to see, would this really happen in a data set where all the supernovae would have the same, more or less, absolute luminosity independent of distance? So we can write a Monte Carlo simulation and ask this question. We did that. These are the steps to construct this. I don't have time to go through these steps for the simulation. The important thing here is that we construct a test statistic sigma m crit, which is the difference between the best fit. We split the supernova into two bins, a higher distance bin and low distance bin. We find the difference between the best fit m on the low distance bin and the high distance bin. And we define this as a statistic to grow the M transition statistic. And we make some Monte Carlo simulations to see if this would happen by accident how often would this happen by accident in a homogeneous dataset of supernova luminosities. And we find that in fact about 6% of the homogeneous samples had this property, had the same sigma max as the real data. So it's not very uncommon, but it's not also extremely common. It's about 2 sigma level. About 630 of the 10,000 samples that we constructed randomly indeed had this sigma max larger than the sigma max of the real data. That means it had a larger transition features than the real data. So it's about a 2 sigma effect for the luminosity itself, but it's something which is not negligible. So since I ran out of time, I don't have now much time. I just show the conclusions. Thank you for your attention.